Okay. Good morning, everybody. I hope Barry's having a wonderful day. So last day, I've been starting to build up a lot of pieces for us. So we talked about what an algorithm is, or at least an understanding that we could talk about when we talk about what an algorithm is. We talked about things like pseudocode. We've seen how we could solve the search problem using linear search. We talked about the idea of proof of correctness. Now, a big other piece of this is how we can compare different algorithms, because that is easily one of the bigger other pieces. If you had an algorithm that's correct, very, very, very slow, and something that somebody in practice, or even just theoretically speaking, is just so dang slow that you would never want to use it, that may as well just be a death sentence to your algorithm being used in practice, unless it's absolutely necessary, which that is something on its own right that is of interest. But that is something beyond the scope of this course. But that brings me to talking about how we can analyze algorithms. Now, correctness is one element of this, but we're going to see that efficiency is another key part of this. So we're going to be laying out a lot of pieces to get us there here today. But before we do that, a very natural exercise in this process is determining how we can compare two algorithms. So like I mentioned, you might have a really, really slow algorithm, but it might be conceptually very simple or easy to implement. That might be a positive thing for us when we think about comparing any two algorithms. So can anybody think of any things that might be desirable characteristics for an algorithm that we can compare? So I guess I technically gave you one idea. Conceptual simplicity is one. Does anybody else have any ideas of what other kind of characteristics might an algorithm have that we can compare between two to say, oh, I like this one seems better than the other one? So I gave you one, like the idea of conceptual simplicity. Efficiency, I see efficiency, I see speed. So I'll include speed, I'll talk about that as running time. Now, efficiency can mean a lot of different things, right? So, and most certainly efficiency can be in terms of like the time it takes. Is there any other kind of things you might think of that on a computer that might really matter when it comes to efficiency other than time? Most certainly readability. I like to think of that something maybe along the lines of, maybe I'll throw that in as the following. I'll think of that more like difficulty to implement. That's a good suggestion. Because if your algorithm's really tough to implement, what if there's like the difference between your algorithms, like maybe like within a narrow margin that you could use the much simpler to understand algorithm that's easier to implement versus this one that's way more sophisticated, but maybe the benefit of implementing it might be a little bit more expensive to do. That may be something somebody might consider down the line, but most certainly that seems to be one thing that we might want to consider. So yeah, readability, accuracy, most certainly it being correct is one that would be very important. User experience. Now that's more on the application side, but most certainly I would say that kind of falls between these two. But I'll give you a good suggestion on user experience. Very often when somebody has an algorithm, if you are solving one problem with that algorithm, is there a natural way for me to take that given algorithm and this is going to sound really funny, but a cat knocked my camera's line down. I'm going to fix that right now. So let me just give me one moment here. Okay, there we go. My apologies. That was amazing. If I can get the culprit, I'll most certainly show you. Right now she's playing with a ball on the ground. I know that was funny, man. But yeah, no, where was I? Yes, my apologies for that. That was the minute I saw it, I'm like, cause I looked at my screen, it's all black. I'm like, what? And then I looked on the ground, like, what the cat? There's a cat playing on the ground near my cords. So I just unplugged it and plugged it in. It was all good. My apologies, everybody. Hey, look, I like to keep surprises going on, and hopefully that was one that you might have enjoyed. I've never had that happen before. I guess there's a first for everybody. Give me one moment, I'll show you the culprit. Come here, you. Yeah, this is Miss Kitty. She's a very cute kitty, but she's very mischievous. She might show up in one of our later lectures. Sometimes she helps me out with a couple of things here or there. Anyway, so let's get back to where we were. My apologies, everybody. Yeah, Miss Kitty is really fun. She's just mischievous. She likes to really get herself into some fun trouble every once in a while. But let's get back to where we were. So I was thinking a little bit about what I was saying. I know, right? When it comes to difficulty for implementation, and somebody brought up about user experience. So when we try to solve a given problem, we have an algorithm that's designed to solve it, right? Well, what if I had that problem and I make a small tweak to it? It would be nice to be able to take the algorithm and easily tweak or modify it to adapt it to solve other problems. So that brings me to talking about, so another thing that maybe we might consider is the idea of difficulty to modify or augment. So is it something that I can easily modify to solve other problems? So just as a good example of this, linear search. So linear search is something I could do on an array, right? I could easily modify linear search to apply it, for example, to a linked list, right? Instead, I would just simply traverse through the nodes. But notice that the structure of linear search is very much the same idea conceptually, but most certainly now I can easily modify it and it does effectively the same thing, just now I'm just going over a linked list as opposed to an array. That's a nice feature of a given algorithm like linear search. Some algorithms don't have a behavior like this. Sometimes they're very specialized. So another one that I wanted to bring up was, we talked about running time. Another one in terms of efficiency might be the space or memory usage. Now, a lot of us don't really think about memory usage unless you really have issues with RAM on your computer, or just generally you need to have it so that you can actually run the programs. Now, there was a time in computing history where space actually really mattered. At the time, there were times where like a megabyte was considered a seriously mega huge, pun intended, it's a mega, like a currency of sort. Just it was that big of a magnitude of storage, even a megabyte. There was times, say back in the 60s and 70s, or in fact even before that, that if I gave you something like that, it would be huge. Just huge. Like I'm not even kidding. Some of these older computers from like especially the 50s and early 60s, some of these machines, it was very common for them to be larger than the size of a room to even the size of a school bus. So keep in mind that the amount of memory they had was also quite limited. So for us, when we think about a megabyte in today's world, that doesn't seem very expensive. But years and years and years and years ago, decades ago, this idea of space usage used to be a really, really important one. Because if your program, for example, or algorithm, if we're talking about its implementation, most certainly that would kill your use of that algorithm if it used too much space. So I think this is a pretty good list we have here. So what we're going to do in this course, now all of these are valid ways of comparing different algorithms. Most certainly. But there's going to be really two that we're going to focus on mostly in this course. But the other ones I might comment on, it's these two right here. The running time and memory or space usage. So these two in particular are interesting to us because they require resources from the computer, right? So these ones actually are ones that when I use the computer, they use resources of that computer, and I would like to measure these on a actual quantitative ground. Now you might say, Dan, how are you going to do this? That's what today's lecture is going to be about. Is how we can do this in a way so that I can talk about the algorithms, not necessarily one given implementation of that algorithm on a computer. So when I talk about these couple of things here, like running time, space usage, these are examples of things that we would refer to as complexity in computer science. So we would like to measure the complexity of algorithms. So that brings me to talk about complexity and what are we, so I want to put these into more clearer terms. But before that, are there any questions before we proceed, other than seeing Miss Kitty again? Because she's already gone. She just kind of bolted off. Augment, it means modify with addition typically. So for example, if I have a piece of paper, if I tape another piece of paper to it, I'm augmenting this piece of paper by including another piece of paper on it. So it's just modify. So that's what augment means. So usually that phrase gets used when you have something that already exists and then you modify it. So for example, you have like a given data structure, you add more functionality to it, or you make a small tweak to it. That's usually what people mean by augment. So question, so do we take into account code security when working on algorithms? Not really, no. So keep in mind, like we talked about the other day, an algorithm isn't tethered to any one computer, nor is it tethered to any one implementation on a computer. So when we talked about linear search, for example, I described it to you in pseudocode. If I were to implement that linear search in C++, it's not confined to the boundaries of that computer. Linear search exists as a mathematical idea that I can easily tell somebody to carry out. So keep in mind that in that sense, we need to talk about the algorithm itself as opposed to just any one given implementation. But if you talk about one given implementation on a computer, most certainly security might matter, right? For example, when you might talk about object-oriented programming, you might talk about the idea of hiding information within classes and using those types of features to restrict the user from using certain aspects of your classes. That's a separate discussion. So hopefully that clarifies that question. That's a wonderful question, by the way. So let's head over here and let's talk a little bit about complexity. Oh, that cat, man. I've never had that happen before. So anyways, let's talk about complexity. So when we talk about complexity, like I said, this is just simply the amount of resources that computer uses. So we're going to be interested in this course in two different kinds of resources, and these aren't the only ones. For example, in different computational systems, there might be other things you might measure. For example, at one point, maybe in your studies, you might be interested in things like distributed computing or parallel computing. These also can bring their own concerns of measuring in terms of resources. For example, if I was thinking about like a computer network, if I have a big computer network, one thing that I would have to take into consideration possibly is the communication cost from one computer to another computer. So that might be another type of complexity I might have to measure in something like a network, which you can think of as a whole bunch of computers put together, just distributed over a bunch of machines. So the two that we're going to be interested in are space complexity and time complexity. So just to be very clear about how we're going to talk about space complexity in this course, is that it's just going to be the amount of memory that the algorithm needs. So I'm going to imagine I give you the algorithm, I give you a problem instance, and I want to know how much space gets used by the algorithm when I run it on that given input. So in this course, I'll be referring to specifically what we call the extra or auxiliary space. Now, classically speaking, the space complexity is normally thought of as the input plus the extra space or auxiliary space. So for example, just to contrast the two, if I have, say, I'm looking at linear search. Well, the input size here, well, we know it's n, right? It's going to be something like n. Well, in linear search, what did I do? I make a variable. Well, that's just some constant number of bits, right? And then I run through the program. My program, of course, is of a fixed size. So if I count up all the memory usage, if I don't count the input in that, then you could tell me that there's a constant amount of memory that is being used, right? Because all I'm using is just some variables, right? I'm not doing anything else other than that. So that will be the way we'll conceive space complexity in this course. But I must stress that classically speaking, the space complexity in that case would include the input itself too. But we will focus on so-called extra space or auxiliary, what is called auxiliary space, the additional space that's used once you start running the algorithm. Very often when we talk about data structures, it'll be the amount of space that's used by the data structure. So that being said, that's space complexity. Time complexity, as the name suggests, is the amount of time that is needed by the algorithm to complete. So notice the usage and terms I've used here. It's the time needed by the algorithm to complete. So there's different ways we might manifest this idea, and those are things we're going to talk about today. But you'll notice that naturally this sounds like it's going to be like the longest that the algorithm might need to take. That seems to be one very natural way of thinking about time complexity, and that'll be the one we'll mostly focus on in this course. And the other notion is this idea of time. That's another thing we're going to parse out today is, okay, what do you mean by time? You're going to see that very much when I mean time, I'm talking about operations, the number of operations that happen. It might actually not be like we're literally counting CPU cycles on a computer, which that's another conception of measuring time. So that being said, how are we going to measure these? And this comes back to our talk about input size. So we're going to measure the complexity of an algorithm by describing it in terms of a function. So what we're going to do is we would normally look at our algorithm. We would try to determine the given complexity. We derive this through an analysis. And we count up, say, for example, in time complexity, we're going to see we just count up the operations that happen. As many as that it might happen for a given input size n. And we derive this as a function, and that will tell us the time complexity so that if I give you any two algorithms, I can look at the time complexity of one algorithm versus another algorithm, and I can ask which one seems better. So this brings me to the idea of a complexity or growth function. So a complexity function, if I call it f, one thing I want to make a remark about is that normally in this course, even though it's technically an abuse of notation, I'll very often use, if I just talk about the function f, I'll usually talk about it in terms of whatever the input is. So in this case, this would be like on the input. So on the input size, to be more precise. So when I say f, I'm usually going to write f of n like that. But I must stress that technically speaking, this is only done as a shorthand because that's also an abuse of notation. Does anybody have any ideas why that might be considered an abuse of notation to write this if I'm not talking about a function f? So I'll keep in mind, I'm going to give some examples of this in a moment. But most certainly, does anybody have any ideas why that might be an abuse of notation if I'm referring to that as the function f? So I'm using this just as a shorthand to tell you what the input of the function looks like. So I'll give you a little bit of a reminder, maybe from calculus or something like that. So a function f, the name of the function is f, right? So that's the name of the function. So f is the name of the function. But what's f of n? What's this? What is that? N is a variable, right? But what is f when I write it like this? F of n, like that. What is that? What is that? Well, it's not necessarily a solution. It's just the output of the function. It's the output of the function, exactly. So I want you just to be aware that technically speaking, if somebody writes this, as we're going to see, there's really two contexts I'm using it. That's why some people call this an abuse of notation. If I write function f, and I write this as f like this, where I write this, what I'm saying is the exact same thing. I'm saying it's a function f on the size of the input n. But remember, there's two different contexts here. I'm telling you what the name of the function is and its input, versus in some contexts, I'm going to actually literally use it as the output of the function. You're going to see that this difference is going to be very minimal. but I just want to make sure, technically speaking, I address it for you. So a complexity function f will be on the size of the input n, where the function is going to be of the following form. So just as a reminder about functions, you can imagine the function just like a little machine. So I have my function, and say this is function f. Now, when I have my function, I put stuff into the function as input. There can be multiple inputs for my function, and it has output. The input in our case is n, and the output is going to be f of n. So in this case, just for those that have not seen this so-called mapping notation before, what it is that n is going to be a positive integer. So that's what the fancy blackboard Z is. First, a fancy blackboard Z here. This represents the set of all integers. If I put a plus as like its exponent, it's not really an exponent, it's just a symbol. If I put a plus there, that means that this is the set of all positive integers. So I'm telling you n is a positive integer. It gets put into the function. And as output, I get what we would refer to as a non-negative, meaning it can be 0 or greater, a non-negative real number. So that's what this blackboard R with the greater than or equal to 0 right there means. Keep in mind that there's a lot of these different symbols. I'm going to try to avoid using too many of these kinds of symbols, but sometimes it's a good shorthand to be familiar with. For example, if you wanted to have a positive real number, you can adopt this plus notation again here, and you'll see I'll use this. If I want to talk about a positive real number, I'll usually write the set of all real numbers, that's what this blackboard R is, and I write a plus right there, just to say it's positive. But that's what this function is going to take the form of. It takes in an integer and spits out a non-negative real number. So that's going to be the form of our complexity functions with minimal exceptions. So normally the reason you might ask, Dan, why is it that it takes in a positive integer? Can't it be like 0? And the answer is, of course, you can define it that way. In fact, sometimes it'll be convenient for us to do that, though the algorithm will never have it where it takes in an input of size 0. So the natural conception for why the input size would not be 0 is because you can imagine it like I have a program where it has 0 operations that happen. It takes 0 time. And that is not very interesting. That's the most trivial program, the program that literally does nothing. And such a program is very hard to conceive if you think of it in terms of programming languages, because if you run a function, technically terminating the function is an operation. So it doesn't make a whole lot of sense to conceive it that way, but sometimes it'll be convenient when we start looking at some more specialized kinds of complexity functions. So just as a quick example of what I mean by this, for example, you might give me a function f is n squared. So that's a complexity function. So notice that every time I give you a positive integer, it gives me a non-negative real number. So this is how we're going to be formulating a lot of our measurements, is we're going to be formulating the so-called complexity function. So are there any questions about the idea of a complexity function? We're going to see tons upon tons of examples of these. So don't, like, if you're like, okay, I don't really, like, I need to see more than just this and that example. Don't worry, we'll be seeing a lot of examples. This will be kind of one of those little things that we're going to kind of pick up over time. So if we're okay with this, I'm going to proceed to talk about different ways we can formulate the complexity function. So I'm going to, for the sake of our time, I'm going to focus primarily on time complexity, but I must stress that you can take the same concepts we talked about the exact same concepts that we talked about, and you can apply them to space complexity too. There was a weird black blip over there I just saw a moment ago. Let's hope we don't run into any more fun, mischievous things that Miss Kitty did. Okay. So To determine the complexity function, you might ask, Dan, like how do you come up with this? And you'll notice something very subtle I did here, is that the complexity function's in terms of the size of the input. So when I take so remember our picture we had from the other day where I had my problem. Remember I had my problem. It has all these problem instances, right? Each one of these has a size, but a lot of them will have the same size. So for example, if I consider the sorting problem, some of them are going to literally be where they all are arrays of length 5. There's going to be ones that all of length 10. There's going to be ones where all their lengths are 30. But they're all in this bubble. They're all in here with all of these dots. So this is where it gets a little bit more difficult for us, because when we study algorithms, I would like to measure the running time of the algorithm, especially if we talk about time complexity. So this is where it gets interesting, because we want to measure the complexity with respect to the input size, if you look at our complexity function definition. So we're going to need some way to tether down these instances so we can talk about them in terms of the time complexity. But each one of them, even though their sizes could be the same, they may cause different behavior for the algorithm. I'll give you a quick example of what I mean by this. So for example, when we have linear search, if I give you an instance where I have key x, and suppose x is in the very first spot, versus another instance where the key is here at the end. Notice that these have the same number of elements, but the inputs actually are going to cause linear search to behave differently. Does everybody see that? So if I did linear search and I scan from left to right in this array, x is in the very first spot, and I would just simply return the position 0, right? How many iterations of that while loop that we had the other day, how many would happen there? It would just check the condition right away, right? The while loop is just like, oh, while I is less than n, and it checks if it's not equal to the first position, right? And it says, okay, well, it isn't, so I'm just going to stop here, and I'll just return position 0, right? So in contrast to this one, notice despite them having the same number of elements in this array, keep in mind these will have numbers in there too. Notice that in this case, x is right at the end, so I'd have to compare this against x, this against x, this against x, this against x. Then I hit x here. But notice despite the fact that they both technically have the exact same size, they both have arrays of length 5. The algorithm behaves differently. So if I want to measure how long the algorithm will take to complete, you'll notice that this one here actually tells you a lot more information than this one does. My goal is to determine how much time is required by the algorithm to solve the problem, right? Is that fascinating? So this is why I'm going to introduce the idea of case-based analysis. So what I want to do is I want to be able to tell you, hey, look, these ones here, because the algorithm will terminate very quickly, right? So I want to be able to isolate every single possible array of a given length n where x is in the very first spot, versus instances that cause this kind of behavior. The ones that cause the algorithm to take as long as possible. In fact, you can make it go, it's not really that much different than if I just didn't even have x in the array and it checks every one of the elements. So notice that if I give you any array of length n, notice that in this case, I only just check the first spot and I'm done, right? That is very different behavior than if, say, x wasn't even in the array or in the last spot, right? So I would like to be able to isolate these in terms of cases. So to determine the complexity function. So I haven't yet really got to the part where we formulate the complexity function. I'm just giving us the framework for our analysis. So to determine the complexity function, we can consider three different analyses. 3 different analyses. So I must stress that these are not the only 3, but something that was brought up earlier that I think that's a nice thing to ease into here. Somebody brought up about user experience. I'm going to twist that sort of on its head and say, suppose I'm studying the problem, and I want to know, if I give you an algorithm that solves the problem, how well does it perform in the most optimistic scenario, such as this? How does it do in the worst case scenario, such as this? This would be like, this will cause linear search to take as long as possible if I had numbers in all of here and they're not X. Or on average. So these are all different cases people might be interested in. So these are the ones that we're going to focus on in this course, primarily the so-called worst case, because that is the one that naturally captures the time complexity that I gave over there. It takes it quite literally, saying that it's the time required to take to complete. So if you take an upper bound on that, the worst case or pessimistic scenario, that tells you how long the algorithm will truly take in the worst possible case. That's the amount of time it requires. But remember, the time complexity can be measured in different ways. We can think of it as a best case, on an average case, or a worst case, for example. So we're going to focus on these 3. So I'm going to use linear search to help explain these ideas. So first is best case analysis. Best case analysis. So my definition is going to be rather straightforward. I'm going to keep it high level so we don't have to get too overly bogged down in definitions. So this is the best case scenario, as the name suggests. So this is just the analysis using a best problem instance. So you might ask, Dan, what is a best problem instance? In fact, you'll notice that the way I describe these examples up here, I tried to generalize them over the input size n, right? So what this is normally described as a scenario that defines a whole set or collection of instances that cause the least number of operations to occur for our algorithm. So just as an example, in linear search, those are when X is located in the first element. I'll say the first spot in L, right? This only requires one comparison. Regardless of how you slice and dice linear search, it does one comparison to check that, oh yeah, X is in the first spot. So just think of best case analysis as you define a scenario that for which every one of the instances described by your scenario all will perform the least number of operations with respect to the input size. So for example here, notice that when I say X is located in the first spot, I can define technically, just to get a little bit heavy on with you, is that if you think of my picture, there could be infinitely many arrays that all fit this form, right? So when you describe a scenario, you're actually telling me a whole bunch of problem instances that cause, with respect to the size of the input, the least number of operations. So that's the optimistic scenario here. Okay, the next one is average case. And I'm not going to focus so much on average case here. I just want you to be aware of what it is. But I'll include a full example in the notes if you're curious about it, because it requires a bit of statistics. So the natural, simple way of me saying this is the cop-out definition. This is the on average. It's on average. Now, what it is it's the analysis using problem instances using problem instances. Instances of a given problem. Of a problem over some probability distribution. Very commonly, it's over a uniform distribution where each instance is equally likely to happen. So usually it's where all outcomes are equally likely. So one common way you can analyze, for example, linear search in the average case is to study so-called what happens when you consider where X could be equally likely to occur in any one of the positions. And that would be one way you can do average case analysis. Now you might ask and say, Dan, well, X could not be, sometimes may not even be in the array. But if you want to measure the number of comparisons that happen in the algorithm, the last spot and not being there are not any different, right? It still performs the same number of comparisons. So I must stress that this analysis requires a bit of statistics. So for some of you, be like, oh man, that sounds like fun. Other students are like, oh, I don't know. Either way, I'm going to include an example of doing average case analysis in the notes for linear search. So just as an example, you can consider where X is equally likely to occur in any spot of L. So if you consider this probability distribution, keep in mind the way that you would define this is that there's going to be a set of instances. Remember my bubble over here. What you can do is you can cleave out all of the problem instances. You can say, okay, these are the instances where in the first position, X appears. These are the instances where X appears in the second spot. I don't know, these are the instances where X appears in the third spot, and so on. And keep in mind, there's infinitely many of these. So it gets kind of weird to think about it, but the mayonnaise and mustard help us think about these things very intuitively. So if you take this over a probability distribution, you can actually show that on average, the number of comparisons that are required in the average case is n+1/2. So it actually still ends up being that it takes a linear number of comparisons that happen. It's most certainly going to be somewhere intuitive, and this matches up with somebody who has an intuition of statistics, that it should be somewhere about the middle, the number of comparisons that happen on average. Because each of these is equally likely, if you think of the number of comparisons, it might be somewhere about the middle. It turns into just a basic average calculation. But yeah, I'll let you take a look at that. I think it's a pretty cute analysis. It just requires computing an average, believe it or not. In the notes, I included a definition for an expected value. So we don't necessarily need that strong of a definition. We just need to compute the average in this example. But I think it gives you a little bit of a backbone if you're curious more about average case analysis. In this course, I'll primarily focus on worst case, best case, and just generally time over space. But average case is something I'll recite or tell you about, and I may give you an intuition behind it. Because sometimes doing those calculations can become either very time consuming or they're beyond the scope of this course. So that brings me to the third one. This is the one that's going to be our best friend in this course, is the so-called worst case analysis. So let's talk about the worst case analysis. So I believe it or not, I actually gave you the intuition behind worst case analysis already. So the idea is that we identify the worst case scenario, which happens to be the most pessimistic scenario that we can have, right? That is the worst that we can do. but that means it's going to take the longest. So this is one thing that I want you to just be aware of. So worst case analysis. So let's look at worst case analysis. So what is that? It's analyze in the worst case scenario. So we're going to see lots of examples of doing this in this course. Analyze in the worst case scenario. So you would describe a situation so that defines a whole set of instances that cause the algorithm to perform as many operations as possible with respect to the input size. So I'll give you an example in a moment that just matches the one I gave you a little earlier. Using worst problem instances. So whereas best case analysis, you try to determine when it will be the fastest the algorithm is going to terminate with your answer. Worst case analysis is the idea is that we want to see how much time is actually required at most by the algorithm. So that brings me to a very important point, which after my example I'll tell you. So just as an example, actually, I think I already gave it in our example, so I was going to ask you guys to figure it out, but I think we figured it out together earlier on, is that in this case, you can either think of it as x in the last position, or that x is not in L. This requires comparing all the elements, right? It requires n comparisons. So notice that if I consider this scenario here, so for example, if I'm working on the assignment or something, you describe a situation that causes the algorithm to perform the most number of operations given your input. So that means that it's going to take every possible path of execution that you can get it to do as many operations as you can. So that being said, the idea is very natural here, right? In linear search, what happens is we're trying to put x as far away from the first place we examine, right? In this case, we're just not even going to include it. So that means it's going to have to check that x isn't in the array. It's got to scan all the way from left to right. We're taking advantage of the ignorance of the algorithm. So believe it or not, at first you might say, Dan, well, that's a problem, right? Like linear search, like, should it be able to do this faster? And the answer is actually it's a surprising cause. If you don't know anything about any of the input in the array L, it doesn't actually make any difference. Linear search is actually the best you're going to be able to do, which is something I usually prove in a course like CS210. So it isn't actually a bug with this idea. It isn't at all. It's just that the correctness of our algorithm requires that we examine every one of the elements. We're just taking advantage of that. So naturally, I want to make sure I give you a note, and I want you to put like 3 stars beside this in your notes because I like asking about this. So that's a big hint. So if we have the worst case time complexity, if we have the worst case time complexity of an algorithm, then you know the algorithm will never, and I mean never, will never run longer than the running time specified by this type of analysis. Why? Because we're being the most pessimistic as possible, right? So, for example, the idea of worst case analysis, when you identify these worst case problem instances, the idea serves both a practical one and a theoretically fascinating one. Practically speaking, you can think of these worst case problem instances almost like benchmarks, So you can imagine you can collect up all of these really bad problem instances, and you can feed them to your computer program, and you can see how long it takes them to solve them, right? So you can look at it like benchmarks. Like I'm trying to see, can it solve them faster? Well, to solve the whole entire problem requires solving these worst case problem instances too, right? They just cause the algorithm to take the longest. So on a practical level, it gives you some intuition for how you might design tougher cases for your program to solve those problems. But it depends on your goal. If you want it on average, you might take some of the intuition from the average case analysis, or you might take, if you want to see how quickly it might solve a given problem, you might look at the best case. You might salt and pepper the whole thing, even with randomized instances even. But the idea is really simple. If you want to know how long the algorithm's going to take, the worst case analysis will give you the upper bound on that. Is that clear, everybody? So you can look at each of these types of analysis as something that we decide upon before we start measuring the complexity of the algorithm. So normally we have to do this is because, like I said earlier, different problem instances can have all the same sizes. Like different ones can have the same size, but it causes the algorithm to behave differently. This is why we're establishing these case-based analyses. So anyways, that brings me to the other piece that's important for today's lecture, is the idea of how exactly do we measure stuff on our computers. That's kind of an important bit to this that I've been keeping off to the side for now, and now I need to start talking about that because it's going to be important for us. So something I suggested earlier is that you can actually experimentally check the performance of your program, which is something very natural to do, right? In practice, you might do this because you might have a target platform or a target computer that you're interested in running these programs on. If you think about their implementations, so if I want to solve a problem, I formulate it in exact terms. And then I design an algorithm that solves the problem, and now I want to see how well it performs against another algorithm. One way I could do that is run a computer program and can test the two against each other and see if it meets the demands I require. That's one thing you can do on a very practical level. But I must stress that we want to look at the algorithm itself, not just its implementation. That's just one possible implementation of the algorithm, right? If I take an algorithm like linear search, I could write it up in C++. I could write up another version in Java. I may even tweak the version I wrote on the board and have it where it has a return statement inside the loop. I might do this, but these are all different like if I take them, translate them into code on an actual computer, this is one given implementation of that algorithm. But that doesn't answer the question of how efficient the algorithm is, regardless if it's on a laptop, on a desktop, a smartphone, wherever it might be. Heck, even if I talk to some people and ask them to do it, how efficient is it? So I need some way of measuring that. So we're going to focus on worst case analysis in this course, but there's one big problem, sort of like the big elephant in the room I have not addressed. However, we need some clock. We need some clock, right, to measure time. Likewise, we talked about measuring space. Very much a similar idea there too. To measure time. And a machine for our analysis. Right, we need both of these things. That seems to be a big problem for us because we have this complexity function. I want to be able to formulate this thing, but also I want to know how long the algorithm takes, right? Now, I got to first talk about the experimental way of doing this, and then I'm going to talk about kind of the drawbacks of this, and I'm going to try to edge you towards the idea that we don't necessarily need to do the experimental approach if we need to study the algorithm itself. So this is in contrast to us applying or implementing the given algorithm. So let's first talk about an experimental approach to this, which is something totally legit. A lot of computer scientists do this kind of stuff all the time. Some do, some don't. Most certainly, This is one way you can do things, and it's totally fine. Just, it's not really addressing the same question that we're looking at in this course up to this point. I just want to make sure you're aware of this practice of measuring time complexity requires often. Well, the first thing you need if you're doing a computer experiment is probably a computer, right? You're going to need a computer. You need a computer. You need an operating system to run your program, probably. Now, depending on how you implement the algorithm, you're probably going to need a compiler for that. A compiler for the programming language, for which the algorithm is implemented. So when you're doing an experimental approach, a lot of different programming languages will have packages or libraries that you can actually use like a stopwatch, so timers or clocks. So a lot of different programming languages will have these, and very commonly what you might do when you're measuring out the time something might take is you would have one of these time functions that you initially start, like a stopwatch, and then you would call it again to see what the current time is, and you could just take the difference of the time when you started and when the time when ended, you can figure out what that difference is, and that tells you how long it took to execute said program. That's one way you can measure the amount of time it might take on the computer. Most certainly, that is one way you can do it on one particular machine with one given implementation. But that brings me to a couple drawbacks about this. But I must stress that doing this with many instances, not even just talking about implementing the algorithm itself, these are time-consuming and expensive to do. Because keep in mind that doing all of these tests, that's going to take some time to do. Yep, that's exactly the other thing I was going to get to. Very interesting observation. Somebody pointed out, wouldn't the amount of time be influenced by the machine itself too? Yes. That's where I'm going. You're getting ahead of me here. That's going to be one of my killer points here, really as a drawback to this approach. Like I said, this is totally legit. You can do this kind of stuff. Normally when people give you computer experiments, they'll tell you usually the specs of the machine and what kind of machine it is. So usually if you pick up like a paper that's doing more of an experimental study, they'll usually tell you what they're using. So you have an idea of what they're using and how you might replicate it. So another issue that I sort of glossed over in here was that, remember, for a given problem, like if I consider the search problem, that's all possible problem instances. And we established the other day, I can't just examine every single problem instance. There's infinitely many of them. So I have to select a subset of those. I got to collect up some of those in a bucket, and I can run those in my test. So just like my case I mentioned over here, you might identify the ones that take the longest and make some benchmark tests. So you might be able to generate these instances yourself automatically by having, say, a way to automatically make them. For example, you could just consider an array and you just keep making arrays that are longer and longer, and you just feed them the linear search, but they don't have X in them. That's one thing you can do, but you can do very much same idea with other cases too. So just remember, you have to recall that we must consider all instances. So I want to know what the complexity of the algorithm is. So I'll say our experiment depends on the inputs selected. Depends on the input selected. So that's one thing that we have to be careful about, is that especially if somebody sets up a computer experiment, you have to be very mindful of the instances they pick. For example, are there goals to try to benchmark to see how slow the thing might take? They might use a worst case approach when they come up with the kinds of instances they make. If they're looking for something that means it sort of operates on a random level, like something that kind of is what you would expect to happen, they might make a random set or a random set of instances that the experiment uses. Like they'll just generate a whole buttload of instances. And yes, I always get the opportunity to say buttload, I will do it. They make a whole lot of the instances, like millions of them sometimes, depending on how big or how difficult the problem is to solve. I've seen papers where the number of instances they use in their experiment is something on the level of, I've seen anything from about 25 to something about hundreds of millions. It depends heavily on the problem you're studying. Sometimes problems are very tough to solve, and even generating instances for them are very difficult to do. So sometimes they're very tailor-made. And the last one is the one that was mentioned by a lovely student. So the results depend on the particular implementation. On the particular implementation. On the particular implementation. And the machine the results are timed on. And the machine the results are timed on. Are timed on. So I have a question for you. If I take an experimental approach like this, is that machine dependent or machine independent? It's dependent, yes, it's dependent. So what I would like to do is try to make it so it's not so dependent on any one given machine. It's machine dependent. So just be aware of these limitations. Yes, that is also another big factor, is indeed the compiler selection. Sometimes there's different compilers are able to optimize your code a little further than other ones will. This is true, for example, when you pick up some compilers that are able to do much more meta-level optimizations. I'm thinking of, the name is escaping me at the moment. So if you take G++ versus Clang, like these will do different processes for how they optimize your code. So that might influence the outcomes when you're timing your results. So either way, the big thing here is that it's dependent on several different things in your experiment. So very often when you pick up an experimental paper or there's a part of a paper that's experimental, they'll usually tell you how they compiled it, what platform they're using, and their specs. So these are things that are important when you do an experimental approach, but at the same time, I also just want to make you aware of the limitations of this and how we're going to try to approach this. So just be aware of these limitations if you do a computer experiment. So just be aware of these limitations. So like I said earlier, you're going to find very quickly that I'm not actually going to be very interested in measuring specifically one CPU cycle or something of that nature. I'm not going to measure the CPU cycles of an actual computer, which is going to sound very strange at first because we're so used to the idea that, oh yeah, we run it on the computer and we can see how long it takes, right? Well, you know how we talked about an algorithm and I try to give you this idea and try to wean you against the idea that we have to think about the algorithm as one specific computer program in one specific language on a computer, right? Well, I'm going to pick up that same idea and I'm going to abstract the idea of a machine. So our goal here will be to make it so that we can study the algorithm itself in a way such that it is not dependent on any one computer platform, regardless of the fact that I don't have to choose or select instances. I can consider all the instances based on the kind of analysis I use. So the idea is I'm trying to make a machine independent approach to doing this. So I'm going to say we will take a machine independent approach, and I'm going to put that in quotes because at first you might say, Dan, what does that even mean? Well, you're going to see in a moment. A machine independent approach. We want to know the time complexity. The time complexity on all inputs, the amount of time we're going to require on all inputs and all implementations. And each one of those implementations depends on several things: the machine, the compiler, the programming language you use, the operating system, the entire platform. We're trying to strip away all of those details so we can just study the algorithm itself. And the solution to this is to invent a machine that is abstracted away from the concept of just a machine. Say if I have my laptop and you have yours, and say you have a smartphone or all of these things, I want to strip away all of those details about just any one given machine, and I want to abstract it into the idea of what we call a model of computation. And I must stress, the main reason why you might say, Dan, why would we do this, is because I want to learn about the algorithm itself so that if I ever implement it, the analysis I have isn't dependent on that computer, this computer, or say your computer. It doesn't matter which one it is. But the thing is that once you've figured out this, then you can start getting into the much more nitty-gritty details where you can actually pick up and do experiments to figure out which one seems more appropriate for your specific case. But generally, I'm interested in just, so do we use a standardized virtual machine? So it's going to be like that. It's going to be like that. But I assure you it's going to be even more abstracted, even away than that. So I'm going to use the idea of a model of computation. So I'm going to define what that is first. I'm going to give you just an idea of what a model of computation is. And then I'm going to give you the rules of the model of computation we're going to use. A model of computation is a formal model. It's that mayonnaise and mustard. It's a formal model that describes computation. As an abstract, describes computation as, let's go with hypothetical. I think that makes it a lot more fun. As a hypothetical. So that being said, you don't actually have to have this thing manifest like as an actual machine. You can just intuit it in a very mathematical way. As a hypothetical computational machine, hypothetical computational machine that has a set of rules, for how the model computes instructions for the algorithm. So here's the fun thing. It was very interesting somebody brought up standardized virtual machine, because that's what we're effectively going to be doing, but we're going to be stripping even further back than just this. We're going to say, hey, look, we don't necessarily need to have it actually on a computer. We could just simply come up with the idea of the computer And at the same time, as long as it fits the model for which a standard computer operates, then it doesn't matter if it's that laptop, this what I have over here, a smartphone, whatever it might be. The point is that there are many, many different models of computation. That's one thing I want you to be aware of, is that especially later on in your studies, especially if you take a course like CS210 or something of this nature, you'll see that there's actually many different kinds of models of computation. Some of them are modeling the kinds of sequential computers that we're familiar with. Others model things like parallel computers. Some model distributed computers. Some even model things that we don't even have yet. It's actually quite fascinating. So we're going to focus on a very common model of computation in this course, and this will be the one that we're going to follow the rules of when it comes to the analysis. And the great thing about our model is it's going to match very much intuitively the same rules that a sequential computer would follow. So this, when I say this, I mean if you ever were to look into this model further and say you have an interest in systems or lower-level programming, it'll remind you a lot of assembly. A lot of the rules in this model of computation match what you might imagine for assembly language. So if you're wondering about that, if you're curious about it, go right ahead. Most certainly I'm not going to ask you about any of those details here. That's far beyond this course. So the most common model that's used in the algorithms literature is the so-called random access machine model. So that's the one we're going to use in this course for analyzing. The great thing is that because we understand the algorithms and the intuition behind the model, is it reminds us a lot of our actual programs. We can measure and count the operations as per very simple rules that follow for our descriptions of algorithms, akin to like our pseudocode that we had the other day, or even if it was a computer program. So we will use the random access machine, or so-called RAM model of computation for analyzing algorithms. So we're going to just only use it for analyzing algorithms. And as soon as you see the rules, you might say, damn, that's surprisingly nice. So the one thing I need to point out is that the random access machine model, this RAM here isn't about, it's about how you can access the memory, akin to something like RAM on a computer. That's where the name sort of comes from. It's the fact that you can access memory in a random access manner. That's where the name comes from. And that's something that our computers do all the time, right? So that being said, I want to give you the rules for this model. And you're going to see that you don't have to get really delicate down to CPU cycles or optimize that further down. The idea here is that we're going to strip away a lot of these things. So earlier on, I mentioned about the idea that time operates much more about in terms of operations that occur. So I'm going to give you the rules for the model, and then that'll be basically where we're going to stop for today. But I'm going to make sure, actually, I think the notes actually are a little bit ahead of where I am. If you want to get ahead on look on the example, you can go right ahead, but we'll pick up from where we leave off here today. So if you're really just dying to see how to use this model in terms of how we analyze the algorithm, be my guest. So here are the rules. It's actually surprisingly simple. So here are the rules for our analysis. And I must stress that this is just a general model for the random access machine model. There are much more specialized versions that you can tailor to very specific needs you might have. For example, we're going to make the assumption I can read an entire word on a computer and I can just feed that right into an assignment. Some computers aren't capable of doing this if the numbers are really big, right? So there are different types of random access machine models that do actually take this into account. We're going to just assume that our model is strong enough, as in our computer is powerful enough to always read the input and do so in the manner that's going to allow this to happen. which in many settings will be appropriate for us. So each simple or primitive, I'll use these terms usually synonymously, each simple or primitive operation takes a constant amount of time. Which this will be used synonymously with operations. So these will often get treated as, treated sometimes as one step or a constant number of operations, which we'll be counting those. So when I say the word constant, what I'm referring to is independent of the input. So for example, if I look at linear search, you know the algorithm, it starts off by assigning a variable I. Notice that I, what happens with I and the amount of memory I use in that case, it doesn't really matter, right? Like, it's just that the only part that matters is actually how much time is taken here. In this case, it's actually going to be that the time actually depends on the length of the array, it seems. But notice that when I do the assignment where I assign I to be the value 0, notice that it doesn't really get dependent at all on the input size, right? We would say that that's a constant number of operations to perform that assignment operation. So here are some examples of so-called simple or primitive operations. These are all the ones we're going to assume take some constant number of operations, or assignment, addition, subtraction, multiplication, division. Any arithmetic typically we'll assume so. Comparisons, like less than, greater than, equals, less than or equal, greater or equal, not equals. Typical arithmetic and logical operations, they all fall under this. So other things like return statements, Boolean as well. Then one thing I need to also say is that subroutines and loops. So I'm just going to finish up here. We only got one more rule after this. Subroutines and loops. So for those that are not familiar with the term subroutine, it's a way of me saying you call a function in your algorithm. Just like when you have a function that's solving a problem, your function might call another function. We would refer to the function that is helping you solve the problem as a subroutine, as opposed to a routine. And loops are not simple. These are composed of many operations. These are composed of many simple operations. And the last thing is that each memory access takes a constant number of steps or operations. And in our computer is capable of using as much memory as needed. We have as much memory as needed. So your computer will never run out of memory. So that's another perk that we get. Now you might ask, Dan, how do we have a machine like this? That's why it's an abstract model, right? But I must stress that the RAM model is surprisingly capable of matching real-world scenarios, despite its simplicity for how we're going to end up counting operations. And next class, we're going to see how we can count these operations. We'll see some examples, okay? So I'm going to stop right here. I want to say thank you very much, and have yourself a beautiful day. I'll see you later.